Hello, in this video I want to talk about the Leibniz Rule. It's otherwise known as Feynman integration, and really in this video we're going to talk about the general case of the Leibniz Rule of integration. There's also a special case, and I'll differentiate between the two, or at least explain the difference between the two in a moment. So what we've got here, this is the Leibniz Rule, the general case of the Leibniz Rule. But even before we get to that, I suppose a bit of preamble is necessary. So it's been noted that there's a general and a special case, but even before all of that, it's worth pointing out that, well, firstly, I mean, on a personal note, the Leibniz Rule is one of my absolute favorites, and if you enjoy evaluating integrals like I do, then it's most certainly an essential tool to have in one's toolbox. And also, more than that, I suppose the reason we can state here why it's so powerful is because it allows one to evaluate otherwise impossible integrals using what we might call more kind of basic methods. And by the word basic, what I mean is kind of like the methods of integration that we learn about in prelim calc, like by parts or by substitution, or whatever. And so what kind of integrals am I talking about here? And well, let's just go over one or two. So think of an integral like this. Okay, we've got some definite integral where the lower limit is negative infinity and the upper limit is positive infinity. And then we want to integrate something like, I don't know, sine x over x with respect to x. Or, better yet, think of something like this. We've got some integral, it's a definite integral, but our limits are more, are constants, something that one will be familiar with as I just introduced the notion of a definite integral. Often you'll use limits that are just constants. So here we've got limits that are constants. We got from 1 to 2. But say we want to integrate something like this, cos tx over t with respect to t. Or finally, to offer one last example, what if we have some integral looks like this? We have to evaluate something that looks like this, where the lower limit is x. The upper limit is x squared, and so we have to integrate something like this, sine xt over t with respect to t. And really I suppose I recommend that you try to evaluate these using kind of the more basic methods. Think of again by parts or by substitution or whatever. Try by reduction even, or you're going to find it incredibly difficult to do that. So in this video we're going to talk about the Leibniz Rule method. It's quite a wonderful operation, really, that will allow us to evaluate integrals like this. So I've already, I think, evaluated all of these in the past. But let's just pick an example. Let's pick one to kind of work through as an example. Let's do this last one here. That looks really nice, actually. Looks like it'll be a lot of fun. And excuse me if I take a break to take a sip of water. It's very hot here in the UK at the time that I'm recording, so I'm going to have to take a water break, such as now. But let's before we even get into this, let's firstly, what I want to do, I'm going to say that I of x equals this. Okay, I'm just going to state that. But before we even start to look at this, let's take several steps backward again, and let's just kind of work through what this is saying, the general case of the Leibniz Rule. And firstly, what it's saying that if we have some integral where the limits are in themselves differentiable functions, right? We've got a function here in the lower limit. Notice, it's just denoted as u of x, okay? If we're thinking about it very generally. Notice that the upper limit is also a function, denotes as v of x, okay? in themselves differentiable functions. And then we have some f of tx, and we're integrating all of that with respect to t. This sets us up for the general case of the Leibniz rule. The general case concerns the situations in which the limits of our integral are themselves differentiable functions, just like this. The special case is where the limits of the integral are constants. The special case is much easier of an operation, especially when one gets the general case sort of down and understood. But I'll save that for a separate video. So right now, in this video, we're just concerned with the general case, where our limits are differentiable functions. You notice here they're functions of x, u of x, v of x. So if we have something like this in this case, it follows then, we'd write I prime of x equals, and this should be I of x really, if I of x equals this. But in any case, so I prime of x equals, we still have our integral, right, with the same limits, upper and lower limits, but notice now we have a partial, okay, a partial that's inside the integral, which is quite strange. And then we've got the partial of our f of t of x, and then we're still integrating with respect to t. Okay, that's very important, and I will explicate all of this just in a moment, and we'll go through why we even have a partial here. But then it follows that we're going to add then our f, and notice that we're substituting here. We've got a tx. We're substituting t for our upper limit, our higher limit, vx. Okay, so we're just going to substitute that in. And then we've also going to multiply all of this by the derivative of our vx, of our upper limit. And then likewise here, we're going to subtract, and we've got f in this, we're substituting t for our lower limit, right, or u of x. And then we're multiplying that by u prime of x. Okay, so this is a lot to digest, clearly. And again, it might seem incredibly convoluted because it's like, well, we've got a partial inside the integral, like where did that come from? And then we're integrating with respect to t. This partial's with respect to x, so it's like, okay. And then we've got all of this stuff out here. It's like, what is this all saying? So let's just start working through it, and we'll start. Well, actually, I'll write it this way. You don't have to write this, but I will, just to kind of show where this partial's coming from. So we're going to write, well, we have our I of x here, so it's going to be that I prime of x equals, and we're going to take the derivative with respect to x of our integral. We've got same limits, of course, of sine x t over t, and we're still integrating with respect to t. Now, there's an absolutely lovely proof of the Leibniz rule. It's beautiful. I love it, and I will most certainly dedicate a video to explaining it, and we'll go over it. But in that, you'll see that the operation is that when we insert this derivative into the integral, like this, we kind of push it in, and it becomes, this is a very important operation as part of the Leibniz rule, and that's where we also talk about, for example, differentiating under the integral, right? So the Leibniz rule, or Feynman integration, or it's sometimes also called just differentiating under the integral. Okay, this is where it comes from. So our important part, we push this d by dx into the integral, and then it becomes a partial. And proof of this is just lovely, but in any case, it just becomes a partial. And so in doing that, we're going to get our general case of the Leibniz rule. So we can say, so here we are, and we can say, by the general case of the Leibniz rule, I prime of x is then going to equal, we push this in, so we're going to have our integral, the same limits, of course. Now we've got a partial here, so a partial, I'll write it like this, a partial with respect to x of our f of xt, which is sine xt, all of that over t, and we're still integrating with respect to t. We can now fill in all of this here. Okay, look what we've got here. That's exactly what we've got here. So we've done the first part. And now we just have to fill in the rest. So we're going to say, okay, plus. We need to substitute our t for our upper limit of the integral, which is v of x, which in this case is just x squared, right? So what happens when we do that? Well, in the numerator, we're going to have sine of x dot x squared. And then in the denominator, we have to substitute for t, that's x squared. And then we need to multiply all of this by v prime of x, so the derivative of our upper limit, which our upper limit is x squared. Excuse me. So if you take the derivative of that, what are you going to get? You're going to get 2x. And then we want to subtract, right? We want to subtract this. Now we have to substitute in. So we have our sine. We substitute in for t. Substitute in for t for our lower limit. So we're going to have x dot, our lower limit is just x, right? That's our u of x term. So sine x dot x over x. And then we're going to multiply that by the derivative of our lower limit, which is just 1. And this is the Leibniz rule. This is the general case of the Leibniz rule. We've essentially just utilized the Leibniz rule. From this point forward, it's just a matter of tidying up, really. We have to tidy up the algebra, and we just have to deal with this partial. Okay, so let's focus on that now. If I scroll down, we're going to need lots of space here. I don't want to skip any steps. So we can just write here that it follows, really, right? I prime of x then equals, so we need to deal with this partial. How are we going to deal with this partial? Well, what if I actually just kind of divide the page a little bit like this, and I write partial here. This is partial, and this will just be our working. Okay, so we need to now take the partial, and to do that, well, we've got a partial. I'll just write it out, right? We've got our partial, something like that. And it's with respect to x, and it's sine of xt over t. And we've got our dt here. We don't need to write this. But I will, just for continuity purposes, if nothing else. You can see what we've got here, right? This is just what we've got right here. And so we've got a constant. It's 1 over t. We can pull that out. So let's pull it out. We still have our partial, like this. But now it's just sine of xt. And what we want to do is, well, actually, now we just have to use the chain rule. This part right here, I box it off for one moment. This part right here, this is just the chain rule, okay? We have sine of u, you take the derivative of that, it's cos u, and then we've got our xt, take the derivative of that with respect to x, it's just t. So, what we end up with is 1 over t, 1 over t, and it's going to be, maybe I'll bracket this, it's going to be t cos x t. Okay, so we've taken our partial. This is also the same as writing it, if I scroll down a little bit more, this is also the same as writing it. Notice, I should point this out actually, notice that these t's will cancel. If one has a key now, you'll notice that these t's will cancel. But let's just not skip any steps. So this is the same as also writing t cos x t, all of that over t, right? So that's what we've got to input here. We just have to input that result in here. I'm just going to take a sip of water. It's very hot. Okay, so we've got our I prime of x. We're still integrating here, right? We're still integrating. We've still got the same limits. Now we just have to input this. So it's going to be t cos xt, all of that over t. And we're still integrating with respect to t. Now we've got all of this. We can tidy some of this up too, can't we, right? Like, we've got sine x dot x squared. That's just going to be sine cubed. Sine cubed. We've got a 2x. That's going to come across like this. And then we can cancel this x with one of these in the denominator. So that's going to be nice for us, actually. If I just create a bit of space here. it's going to work out very nice. I'm not sure if you can see that, but it's going to work out very nice because now we've just got an x in the denominator, and we've got an x in the denominator here. So we've got a common denominator, and this is just sine x dot x, right? So sine x squared. Just put it in brackets, and yeah, we've got an x in the denominator. So we've got a common denominator here. That's beautiful. The thing about the Leibniz rule, it's not really magic at all. In fact, you know, after applying the Leibniz rule, the hope, and really sometimes it is hope, and hope when they're working with a quite a complicated integral, the hope is that that things will start simplifying, you know, and then we can use some basic methods like substitution, and which is what we're going to have to do actually in this case. And the algebra will tidy up, and then we'll, you know, come to something that looks sensible for us. But okay, so so the next line, what are we going to do? We have to deal with this, really. We have to integrate this. So we're going to have to use substitution before we do anything. So as noted, these t's cancel. So now we're only integrating here cos xt with respect to t. Okay. So if I'm going to have to scroll down again a little bit more here. So yeah, we need to deal with this. We actually need to we need to deal with this now. So we're going to have to use substitution. If I just continue this line down the page, maybe I just box this off like this, and I just write substitution. This will be our working. Substitution. This will be our working for this part. So we need to use substitution. Let's say that we'll use u equals xt. Then we're going to take the derivative of u, so du by dt. Yeah, I think, yeah, du by dt here will work, right? So we do du by dt, and that's going to get us x. And then we want to, basically we want this dt by itself, right? So we want to substitute for our dt here. So how do we do that? It's just a bit of algebraic manipulation. We multiply, I'll just scroll down a little bit more. We multiply by dt. Yeah, du equals x dt. Divide by x, you're going to get 1 over x du equals dt. We substitute this in for our dt. So let's write it all out. So we'll just say equals, we're still integrating. We've got our x, we've got our x squared. I'm going to take a sip of water, pardon. So we've got our x, we've still got our same limits. We've got our cos xt. Now we're substituting for this dt, which equals 1 over x du, so 1 over x du. But we can just save ourselves a bit of work, because this is just the same as it said. This would be cos xt over x du. So let's just do that. I'll write it like this: cos xt over x du. And so that's substitution done. Now we're basically ready to integrate this, but notice we're going to be integrating it with respect to u, and actually this is wrong. This should be cos u, sorry. It should be cos u. We perform substitution like this. Now we're integrating this with respect to u, and we are almost done, actually. So we've got all of this here on the right, like this is all the same. We know we've got r2 sine x cubed over x, and we're taking away a sine x squared over x. Alright, cool. So, now we just need to integrate this, don't we, with respect to u. So, how do we do that? Well, I mean, integrating this is quite simple. I mean, we know that u equals xt, so we're going to substitute that back in. And then we integrate cos, that's just going to be sine, right? So, this is where we integrate. This is where we're going to enter, if you watched my other video on a definite integral, we're going to enter the after integration stage. So we're going to have sine, and it's going to be xt, and then over x, all of that's over x, and then we've got to restate the limits of our evaluation. Now remember, we are integrating here with respect to t. At the very top, I of x equals, right? Integrating with respect to t. It's very important because we're integrating with respect to t. We need to restate our limits of the limits of our integral, and that we will evaluate all of this by saying that t equals x squared and t equals x. This is a very important part. And we just, everything on the right here is just the same. So we've got 2 sine x cubed over x. We've got sine x squared over x. Right, and so yeah, now we are basically done here. We just need to evaluate where t equals x squared and t equals x. So this is the evaluation stage, just as one would learn when they're just first introduce the process of evaluating definite integrals. So we've got our round brackets. We need to evaluate where t equals x squared. So it's going to be sine of x dot x squared, right? T equals x squared. All of that is still over x. And then we are subtracting. We've got our sine, and it's where t equals x, so it's going to be sine x dot x. And you might be able to already see how this is just simplifying so nicely for us, because look, we've got a common denominator now right across, which is lovely. So we've got we've still got our 2 sine x cubed over x. We're going to take away a sine x squared term. Should put that in brackets actually, over x. Right, so yeah, I mean, look at it. We're just taking, look, we've got sine x cubed term here. We've got 2 sine x cubed term here. That's 3 sine x cubed. And we've got a sine x squared term here. We're taking away another sine x squared term. So what we've got is 3 sine x cubed over x. And we are taking away now 2 sine x squared over x. And we could keep it like this, but we can simplify it further actually. We just pull out a 1 over x. And what we end up with when we do that is we get 3 sine x cubed minus 2 sine x squared. And we are done.